Welcome back. So we're kind of starting towards the end of our semester, and so this last half of the semester is going to pertain to the atmosphere. These last four chapters, including chapter 11 here, today's lesson, heating of the atmosphere. And so we will be taking a look at the sort of structure of the atmosphere, and then in later chapters kind of look at the circulation of the atmosphere and how that sets up our weather patterns, severe weather, and different topics like this. But this will be sort of the atmosphere portion of the Earth and Atmosphere course. And so we want to dive in and take a look at how the atmosphere actually does get heated. So there's a bit of a process going on in there. And so we'll take a look at some beginning terms here. Weather versus climate, they're kind of similar. However, we talk about weather, we talk about sort of the weather elements, the elements of weather. And so our meteorologists are data hungry people, and they will be taking various measurements using instrumentation to keep tabs on the weather. And so weather is over a very short period of time, moment to moment. You step outside, what is it like? Is it sunny? Do we have cloud cover? Is it raining, snowing, thunderstorm, that sort of thing? But over a very short period of time, and it is constantly changing, moment to moment. Climate, on the other hand, is averaged over a long period of time. It does involve those elements of weather that we'll talk about in this unit. So, cloud cover would be one, wind speed, wind direction, pressure, humidity, all of these elements, but over a longer period of time. And typically it is averaged over 30 years, all of that data. So sort of the average sort of monthly rainfall or something like this, but averaged over 30 years of data. So it's really over a much longer period of time. And so this is more of a generalization, generalized composite of weather for a certain location. What is the climate for your region or something like this? So a little bit different scenario there. Climate's kind of what you expect for a region, and weather is what you get. So that doesn't always match up. Sometimes, you think you want to plan for the sunny beach scene of Florida, right? Sunny Florida, the Sunshine State. Well, sometimes when you go and you book your vacation, it rains all week, something like that. So yes, climate is what we expect for a region, but weather is what you actually do get. So here are those elements of weather and climate that I was mentioning. And these are properties that are measured very, very regularly. That's sort of the life of a meteorologist, is to measure these, this empirical data that they will be collecting. So most important of the weather elements are temperature, of course, and something we call humidity, which we'll take a closer look at. And this is any kind of measurement of the amount of moisture, water vapor in the atmosphere. That's humidity. Cloudiness, so do we have cloud cover? How much cloud cover? Partly cloudy, is it overcast? That sort of thing. Precipitation, and a variety of precipitation. You can get rain, hail, sleet, snow, all varieties of precipitation. Air pressure, and so air pressure becomes very important. We set up sort of gradients of high pressure, low pressure systems, and how those actually do affect our weather systems that trek through the United States. Sets up the atmospheric circulation, or these pressure cells. So air pressure, very important to keep track of. Wind speeds and wind directions. So something like a wind direction in general, living here in Arkansas, if we get southerly winds, that's actually to our south going to be bringing warm Gulf kind of moisture laden air. Okay, versus if it was coming from the north, you're getting more of that polar or Arctic type of air coming down with a north wind. So really, depending on what your wind direction, you can kind of set forth a little bit of a forecast of what type of weather might be coming when we look at wind speeds and wind directions. Those can be quite important. So these are the elements of weather that we will kind of be taking one by one as we go through our atmosphere kind of unit over these next several chapters. Okay. Air is actually a mixture, so it can be considered a mixture of discrete gases. Some are in fixed kind of amounts, others are variable amounts, and so the major components of what we would say clean, dry air, meaning we're not considering the water vapor content at this point, but for clean, dry air, nitrogen is your primary, your most abundant gas. 78% is nitrogen. And then we have a good amount there of the oxygen or the O2, see O subscript 2 there, that's the symbol for the diatomic molecule oxygen, 21%. And then we have some argon in there would become next, abundant, very small amount though, and some other gases. Some that can be, can change over time and have changed over time. Carbon dioxide, so CO subscript 2 is the chemical formula for carbon dioxide. So a very small, much less than a percent there, 0.036%. Somewhat variable because our carbon dioxide parts per million has been increasing over time. But this is an important gas in our atmosphere. It does absorb heat energy from the earth. So as the solar radiation is coming in, various surface features will absorb some of that solar radiation and re-radiate it as terrestrial radiation. We say it's actually infrared radiation. Well, carbon dioxide will absorb infrared radiation and re-radiate some of that back down to Earth's surface. In a sense, it is warming and sort of trapping the heat energy downward, okay, to continually heat. So it's what we would term a greenhouse gas. It's a pretty major one alongside of a few other greenhouse gases. We'll kind of talk about that greenhouse effect in just a little bit. But carbon dioxide, a little bit variable in there. And it is one that will absorb heat energy from the earth very well. So it does act to kind of trap heat in our atmosphere. So here's sort of a pie chart of the composition of various gases, that mixture of gases in our atmosphere. So you're seeing there nitrogen is the bulk of it, right? And then oxygen about 21%. But yes, due to that little very small amount, so the amount honestly, isn't, it can be in a very small amount, but it doesn't mean that it's insignificant. That little sliver of carbon dioxide there is, we talked about kind of global warming and how this is a human-induced environmental problem. So we can get sort of a global warming, a trapping of that heat by the buildup of carbon dioxide in the atmosphere. So that global warming is due to that buildup of carbon dioxide in the atmosphere. So very important in absorbing that heat into the lower atmosphere. One is carbon dioxide, and we will find that the other very important one, probably the primary one, is water vapor. So water in the gaseous state. These are all gases in the atmosphere. So a mixture of gases. So here's your water vapor, and this is very variable depending on region, of course. Well, up to about 4% the volume of air. Okay, so can be very, very small amounts, can be up to about 4% of the air's volume. And so this part of the water cycle, the hydrologic cycle, is that we do get water vapor up into the atmosphere. This sort of help to complete that hydrologic cycle that we talked about earlier chapters in there. But of course, this allows for the formation of clouds and then the precipitation, how we're getting that water back to the land surface. But it absorbs heat energy from the earth as well, and it is a principal primary greenhouse gas. So these are very important heat absorbing gases in the atmosphere: carbon dioxide and water vapor. Okay, very important. So these other kind of minute little particles, sometimes they're little solids, sometimes they're just droplets that we do call aerosols. So tiny solid and liquid particles, they're known as aerosols. And so water vapor will condense on these little solids. These are actually, again, something that's in a very small amount, but very, very important, because that water vapor, in order to condense, meaning turn from a gas back to a liquid and become a little condensed droplet, they need something to condense on. And so that particulate, little solids, allows the little dust and soot particles in the atmosphere, allow that water vapor to condense and form clouds. It's like a cloud condensation nucleus that we will talk about in later chapter. But that's a very important part of the atmosphere, is to have those little aerosols. So something for the water vapor to condense on, little dust particles, think of that. Also, these will kind of reflect the sunlight, they will actually scatter the sunlight. And this is what the dust in the atmosphere gives us some of the most gorgeous colors for our sunrises and our sunsets. The more dusty the atmosphere, the more deep reds and oranges you're going to see in your sunlight or in your sunsets or sunrises. So that's a result of the dust in the atmosphere, those little aerosol solid particles that give you the beautiful oranges and reds, those colors of the sunrises and the sunsets. So little aerosols, okay, very important, very small amount in the atmosphere, but yet they have a very important role, especially in getting water vapor to condense, right, into the liquid, onto those solid particles. Very, very important in our cloud formation process that we'll learn about. Okay, so ozone, we mentioned in the introductory chapter a little bit about ozone. So ozone is known as a triatomic, so meaning a 3 atom, right? 3 atoms of oxygen. So it's an O subscript 3, as you can see from your PowerPoint there. It's not an even distribution. We've actually mentioned the human-induced kind of activity that is depleting the ozone. This was a problem we started to notice. It was really like a thinning of the ozone layer, which is a very important layer in our atmosphere. Those chlorofluorocarbons that we were using in our refrigerants, right? The Freon and stuff like that. CFCs, we call those for short. But these were depleting the ozone. So the chlorine was hooking up with some of the oxygen and not allowing the O3 molecule to form again. So it was disrupting the formation of the ozone layer. So we've banned the CFCs, and so we're hoping to regenerate more ozone. But a very big problem with that sort of human-induced environmental problem of the ozone depletion ends up being this problem of more skin cancers, more cataracts, because if you recall, the ozone is what is absorbing the harmful UV radiation, the ultraviolet radiation from our electromagnetic spectrum. We'll take another look at that. But these are rather short wavelengths in the ultraviolet wavelength. These, for the most part, do get absorbed. There's a variety of them. UVA, UVB, and UVC. All of the UVC, which are very damaging rays, are blocked by our atmosphere because of the ozone layer, but a little bit of UVA, a little bit of UVB does get through, and so we need to wear that sunscreen, put on the sunglasses, and protect ourselves. But this can increase skin cancers as well as cataracts. So that's because if we have a depletion of that ozone, it's not able to do its job. And so what it tries to do is absorb those harmful UV radiation from coming into our atmosphere. It basically does filter out most of the UV radiation. Oxygen does as well, but primarily it's the ozone, the O3 molecule. So that good ozone, that is way up in the atmosphere, between 10 to 50 kilometers above the surface. And we're going to learn that layer in the atmosphere is known as the stratosphere. And so that's way up there, 10 to 50 kilometers up in the atmosphere. Very important composition of the air, the atmosphere. And we have done some damage to it. And the problem is those CFCs, once they're up there, they continue to cause problems. It's that we have banned them so that we're not adding anymore. So we're hoping that the ozone can recover, but we still have some up there that is just going to continue to disrupt the ozone molecule. So we've got the ozone up there as well, a variable kind of component, but a very important one as well. So that hole in the ozone could increase our chances, and has increased chances of skin cancer because it's not doing as well a job of blocking the UV radiation. So and a very important component is the ozone in our atmosphere. Okay, that's a bit on the composition. So this mixture of gases, that's our atmosphere. And so here's looking at the structure of the atmosphere. And we've got a couple ways that we do kind of categorize and look at the atmosphere. One of our kind of weather elements is pressure. Pressure changes with altitude, so as you go up in the atmosphere. The other is temperature that we'll look at, and we kind of separate into layers, even though it's sort of a transitional phase there, according to temperature in the atmosphere as well. So kind of looking at the atmosphere in the vertical, the structure of it. So we do have pressure changes. Pressure, of course, is the weight of the air above. So we've got this nice mixture of gases. Of course, gravity is pressing in on that. It concentrates most of the gases towards the Earth's surface. So we would say at sea level, right? That would be where the pressure is greatest, at sea level, and it's slightly more than 1,000, what we would call a unit of millibars. So millibars are really the unit that we use in for meteorologists that use this term for pressure, millibars, okay? But maybe you're a little more familiar with the English units of about 14.7 pounds per square inch, or PSI. That's abbreviated as PSI, pounds per square inch. So it's 14.7 pounds per square inch, and this is right at sea level, so kind of our lowest level on the Earth's surface. But slightly more than just about 1,000 millibars, and it's actually 1,013 millibars at sea level, we would say. And these are pressure units. And so most of that, yes, gravity would be compressing that sort of mixture of gases, and it would be the heaviest or the most pressure right at the surface there at sea level. Okay. And so that's sort of the average sea level pressure. Of course, we'll have different pressures according to altitudes and terrain and topography and that sort of thing. So the general trend here is for pressure to decrease with altitude. So as you go up in elevation, you have less and less gases, right? They become more stratified gases. And so your pressure is decreasing with altitude. Okay, and then if we look at the vertical, in the atmosphere in the vertical, 1/2 of the atmosphere is below about 3.5 miles. So like 50% of those gases of the atmosphere are really concentrated in there below 3.5 miles. That's where we got half the atmosphere, the density of the gases. And in metric, that's 5.6 kilometers. Okay. 90% of the atmosphere is below 10 miles. And so we have 90% of the entire atmosphere below 10 miles or 16 kilometers. So it does become less and less dense as you go up in altitude. So there becomes less and less pressure as you go up. So pressure changes. It does decrease as you go up in elevation. Okay, and here we have Mount Everest for kind of our topographical feature, right? And so then they've got pressure in MB, so millibars. Really, we do use that unit most in millibars. And then they have the altitude on this side in miles, if you like miles, and on this side in kilometers, so if you like kilometers for your unit there. But we see how pressure is changing as we kind of go up. So right at kind of sea level, be the base of the mountain at sea level, right at about 1,000 millibars, right? And that pressure is going to steadily kind of decrease as you go up in elevation. So I don't know if you've traveled in mountainous terrain, but as you go up in elevation, do you ever feel your ears kind of pop a little bit? That is due to pressure changes as you go up in elevation, and your ears are trying to reestablish pressure in there. So it is kind of decreasing as you go up in elevation. Here, where we're saying that little dash line there is showing us where we have 50% of the atmosphere lies below that 3.5, something like that, miles, okay, of elevation. That's where most of the atmosphere is, and it becomes thinner and thinner. Those gases really thin out as you go up. And so as we continue to go up, right, in elevation, pressure is decreasing, decreasing, decreasing as you go up, and eventually those gases just sort of mix into outer space, we would then call it. So yeah, it becomes thinner and thinner and thinner, less and less pressure as you go up in altitude. So pressure variation with altitude definitely decreases as you go up, okay, in the atmosphere. So that's sort of a pressure look at the pressure changes with height. Okay. So another, here we go, weather element is temperature. And so we'll look at the structure of the atmosphere based on temperature. And so again, in the vertical, so as you go up into the atmosphere, we kind of talk about these atmospheric layers, and they sort of transition and grade in one into the next, and they're not really, you know, fixed kind of positions. They'll vary depending on what's going on with your terrain below, but in general here, we have, based on temperature though, the troposphere is the bottommost layer. So from the Earth's surface and up a little ways, and that distance will kind of change. Average height is about 12 kilometers, but that will vary again, kind of depending on what's going on beneath. But the temperature will decrease with altitude. So as you go up in the troposphere, and of course the troposphere is where all the weather takes place. Our clouds, our precipitation, all our weather happens in the troposphere. That's closest down to the Earth's surface, the bottom layer. And so temperature is going to decrease with altitude as you go up in the troposphere. This is called the environmental lapse rate, how it cools with altitude. And so on average, if you want that in kilometers, it's 6.5 degrees Celsius per kilometer. You'll get a drop in temperature by 6.5 degrees Celsius for every kilometer that you go up in altitude. Okay, if you want that in English units, In Fahrenheit, that's 3.5 degrees Fahrenheit per 1,000 feet on average. Okay, so I don't know, maybe the metric one is what I like to use, the 6.5 degrees Celsius per kilometer. Okay, and that will change approximately as you're going up per kilometer through the troposphere. Okay, and then you kind of get to the outer boundary and they call a pause there. So they call it the tropopause. This is where we start to see a different type of change of temperature. So they kind of call it the tropopause, the uppermost layer of the troposphere, that outer boundary, and things start to change a little bit. Here we were decreasing in temperature with height, okay, on that environmental lapse right there. And once you get to that tropopause, temperatures kind of pause, and they remain kind of steady for a little while. And then they actually start to increase again. Instead of decreasing, they'll begin to increase. And so that next layer where there is a little change going on in the atmosphere, we call it a different layer. And this one will be called the stratosphere. So we mentioned the stratosphere. This is where the ozone layer is. And so that starts at about 12 kilometers where the troposphere stopped. And now the stratosphere begins up to about 50 kilometers within the altitude of the atmosphere. And now temperatures you're going to see are starting to increase at the top, towards the top of the stratosphere. Okay, and then we go through a little bit another change happening. And so the outer boundary of the stratosphere is called the stratopause. And then you get in the mesosphere. Okay, this is about 50 kilometers to 80 kilometers in altitude. And here we go again, temperatures are decreasing now with altitude as you go up. So another little change in temperature, and we call that the mesosphere. And then, of course, the outer boundary to that one is the mesopause. And this is kind of where the meteors go flashing and streaking through. We might see them in there. This mesosphere and then mesopause. And then there's one more layer as you go up, the thermosphere. And of course, this just kind of gradates out into the space, kind of just blends into the space. But there's really no well-defined upper limit. It's a very small fraction of the atmosphere's mass. Gases are moving very rapidly at high speeds, and so temperatures are going to increase again. And so you're getting sort of this change, through temperatures where you're getting differences, and then we're just sort of, because humans like to categorize things, we have called them sort of different layers, atmospheric layers, based on temperature. In this case. And so here's sort of the thermal structure of the atmosphere, a nice little side view diagram of that. Here we go, we're looking, again, they've got Mount Everest in there, but the troposphere, that lowermost part, a layer of the atmosphere, that's where all the weather takes place. You can see the little clouds in there as well. But notice what happens to temperature. So temperatures across the bottom, altitude is in miles on the right or kilometers on the left, whichever you like there. Two different temperature scales. We've got the top one here is in degrees Celsius and the bottom one is in Fahrenheit, so whichever scale you like there as well. And so troposphere, you can see from our red line here how we've got temperatures decreasing with altitude in your troposphere. Then it goes to this little pause where, temperatures remain a little bit steady there. And then we have temperatures decreasing, or increasing again within the stratosphere. This is also where our ozone layer is located, in the stratosphere. Then you get the stratopause, so this remains kind of steady with height for a little bit. And then we begin decreasing temperature with height in the mesosphere. And there's a little meteor coming through the atmosphere there. And then it remains a little steady, mesopause. And then we've got, again, a increase in temperature in the thermosphere. That's kind of a region where we're seeing the aurora, a lot of ionized, very fast-moving gases and particles up there, creating those beautiful auroras the northern and the southern lights in there. Way up there in the thermosphere is where that would occur. And so here is that thermal structure of the atmosphere within the vertical, those changes of temperature as you go up in elevation. And we just sort of categorize troposphere, stratosphere, mesosphere, thermosphere as you go up. Okay, so differences, changes between pressure, changes with temperature as you do go up in altitude. Okay, so that's sort of the structure basis of our atmosphere. Okay, and so Earth-Sun relationships become very, very important in regulating kind of how much solar radiation we are intercepting. And so it has to do with Earth rotation and revolution, a couple terms here. The rotation, let me find my got my model here again. This was the moon, if you remember that from our last talk that we had. But couple motions of the Earth, two motions. We do have the rotation on the axis, right, of the Earth. This gives us our daily 24-hour cycle, day and night cycle, the rotation. And it does rotate on its axis, and that axis is tilted. I don't know how well it's showing up on that model, but the axis is tilted by 23.5 degrees, so 23.5 degrees. It's got a fixed tilt to it, and that tilt basically stays the same. It's not wobbling like that. It is staying in that fixed position as it orbits and revolves, is our next term, revolves around the sun in its orbit. And so we have the Earth revolving around, right? And that would be 365 days just then. So that's sort of how we've got a revolution, okay? That's revolving, okay, around like that. Okay, and so you've got those motions, right? And because of that sort of fixed tilt, this will give us some changes in sun angle as we go through the year, okay, that revolution, and that will change the length of your daylight as well. So those kind of things together, those seasons, are the result of changing of sun angle, which is going to change the intensity, and the changing of the length of daylight, the duration of the amount of solar radiation that can be being absorbed by the Earth's surface. And so that change in sun angle, let's see if I can find something here, but I've got a little flashlight. And here I'm holding that, I don't know why you see me holding this, but I'm holding this sort of directly overhead. So that's a very high sun angle. That is a very intense beam. So great intensity of solar radiation. If I kind of lower my flashlight and I've got a low sun angle here, okay, see how my light spreads out, becomes more diffuse. And so this would be a less intensity of solar radiation being absorbed at the surface. And so sun angle will change the intensity of solar radiation that you're getting. High sun angles, very intense. Lower sun angles, less intense solar radiation. So that change in sun angle is definitely one factor that is going to help us get our seasons and the length of daylight. So if you notice how in the winter months you start to get shorter and shorter daylight, right? Maybe on the order of 9 hours of daylight, you know, around here. 9 hours of daylight in the wintertime, and then you go towards summertime and you're getting onwards of 14 hours of sunlight in our day. So yes, there is a change, a seasonal change in the length of daylight, and it is really all due to the Earth's orientation to the sun, that little tilt in there, in that fixed position. Say this is the sun right here, and it's going around the sun like this. It's changing the position, okay, that Earth is tilted toward or away from the sun, okay? And so this will give us different sun angles throughout the year. and that will cause the season. So it's really two things that are happening: the changing in the sun angles, which is intensity, and changing in the length of daylight, so the duration of the solar radiation. So we've got a comparison here on a couple dates, very important dates in our seasons. So this is at a kind of a mid-latitude, 40 degrees north latitude. So in the northern hemisphere, we live in the northern hemisphere here. Monticello's at about 33 degrees north latitude. So this is sort of mid-latitude in June, and the June 21st or 22nd. And these are very important dates. These are seasonal change dates. So June 21st or 22nd is called the summer solstice. Okay, right there. The summer solstice. This is when we would have our longest day of the year. And this would actually be our summertime here in the northern hemisphere. And the funny thing about these seasons is it's exactly opposite in the southern hemisphere. While we're enjoying our summer and sort of our longest day of the year, in the southern hemisphere, this becomes their winter and their shortest day of the year. So the seasons are opposite in hemispheres. And so in the northern hemisphere, on June 21st or 22nd, there's a discrepancy of a day in there that happens. This is called the summer solstice. This is the longest day of the year, so the longest duration, length of daylight. And look at our sun angle. So our sun angle is 73.5 degrees from the horizon, right? That's sun angle. That's a very high sun angle for mid-latitude region. Very high. That's the highest point that the sun would get throughout the year on the summer solstice, June 21st, 22nd. So you have very high, very concentrated sun angle and a long duration. Okay, so high intensity and long duration, long day length together makes that, you know, like our warmest kind of day. And so that's the beginning or the first day of summer, the summer solstice. So that's an important date in the atmospherical seasons that are occurring, the sun-earth relationships. Now in contrast, then 6 months later, again, northern hemisphere, 40 degrees north, so a mid-latitude, but December. So December 21st or December 22nd. This is called the winter solstice in the northern hemisphere. So it's when we have our shortest day. Okay, so December 21st, just this last December, and the shortest day, so the fewest daylight hours, right? So not very long duration of sun. And look how short or how low these sun angles are. Okay, only 26.5 degrees there. So a very low sun angle, so a very diffuse sunbeam coming down. That radiation is kind of spread out, so it's not very concentrated. So there's not as much solar absorption going on because of that small sun angle in there. So low intensity, short duration, that combination gives us our colder kind of temperatures in the northern hemisphere. Of course, they're having summertime in the southern hemisphere on this date. But in the northern hemisphere, this is the winter solstice. Very contrast, great contrast. So let's look at those sun angles, relationship of the sun angle and the intensity of the solar radiation. Right here, we've got a location that is very near the equator, okay? You have really high sun angles, 90 degrees, nearly 90 degrees sun angles. See, look at that right angle, 90 degrees sun angle, a very concentrated sunbeam. So yeah, you get very warm temperatures there out over the equator and the tropics region, right? They got the palm trees there. So very high sun angles turns into very warm temperatures. Here, kind of a mid-latitude region, we've got about a 45 degree sun angle, right? So moderate kind of temperate climate there. Here in the polar region, so they got a little igloo there, very low sun angles, about a 30 degree sun angle, and so very low intensity of your solar radiation, and that's going to, of course, be very cold, translate into cooler temperatures, like a polar type of a region. So this just looking at different latitudes and the variation of solar sun angles, and of course the intensity of solar radiation, translating into then warmth or temperatures, right? That will change your temperatures. So seasons. Reason for the seasons. It's caused by Earth's changing orientation to the sun as it is going around in its orbit, revolving around the sun. Okay, let's see. We're going to start, what are they going to do? They're going to start at the summer solstice here. But we've got an axis that is inclined 23.5 degrees, and it will stay fixed like that. It's going to stay fixed. Notice how that axis stays fixed, okay? In the revolution, it stays fixed like that. And so, because that is inclined 23.5 degrees, it's always pointed in the same direction. So it's not wobbling around. It is staying, maybe I'll use my other little guy. Okay, it is staying in that same fixed position as it goes around the sun. It stays fixed, okay, as it goes around. So they are going to talk about special days, and we are talking all kind of northern hemisphere here, but I'll kind of throw in some southern hemisphere because those are going to be opposite of the northern hemisphere. But some special days. We already looked at the June 21st, 22nd date, right? That was known as the summer solstice. So on that date, June 21st, let's say, the sun's vertical rays are located at what we call the Tropic of Cancer. The Tropic of Cancer, if you look at latitude, I know you can't see it on this little model, but if you look at latitude, okay, it is 23.5 degrees, okay, north latitude. There's your equator. 23.5 degrees north latitude. The sun's rays are directly, meaning perpendicular, 90 degrees above, okay, on that date, okay? They're right there, okay? So the sun's vertical rays are located at the Tropic of Cancer, which is 23.5 degrees north latitude. That's a very special parallel of latitude. So for those of you in lab, that's a very important one. The sun's rays are directly overhead on that date. The northern hemisphere is a very special atmospheric location of what's happening. Sun's direct rays are vertical, but this becomes what we call the summer solstice, the first day of summer in the northern hemisphere, okay, on that date. Okay, of course, you've definitely got longer daylight at this time. And that's going to translate into warmer, kind of warming temperatures, longer day length, very high direct intensity of your beam. So this all translates into the warming of the atmosphere. Okay. And it also is going to show you length of daylight as well. Of course, we would have, onwards of 14 hours of daylight, so duration is very long during the summer solstice. Another date to remember is the December 21st or 22nd date. That's known as the winter solstice. So if we went another 6 months kind of around here, let's see. Yes. So for this one, notice how the Earth is tilted away from the sun just a little bit to where now the direct rays are hitting at 23.5 degrees south latitude. That is known as the Tropic of Capricorn. So the sun's rays are direct now over here in the southern hemisphere. So guess what? The southern hemisphere is having their summertime. But up here in the northern hemisphere, we're having very low sun angles here, right? So that becomes less intense radiation, shorter day lengths, and so that becomes our, in the northern hemisphere, winter solstice. The southern hemisphere, that's their summer solstice. That's where the direct rays are, okay? right over there in the southern hemisphere. But up here, we're getting a very diffuse angle, right? Low sun angles, shorter duration, less, 9 hours of daylight, all translating into cooler temperatures, okay? So that becomes, in the northern hemisphere, the winter solstice. Okay, then you have a couple dates, and I kind of advanced 6 months in there. So if we started back at the summer solstice, right, where we're hitting it 23.5 degrees north latitude, right, Tropic of Cancer. Let's just go up 3 months, 4 months in advance here. Here we go, here we go, here we go. Well, right now, this is one of these, what we call an equinox. The autumnal and vernal equinoxes. And so on about September 22nd, 23rd, in there, you're getting the sun's vertical rays, meaning being directly overhead, 90-degree angle, at the equator, okay? And so now they're at the equator there, okay? Directly at the equator. The Earth is neither toward or away the sun, and those direct rays are hitting at the equator. This is an equinox. Equinox stands for equal night. And so we would have 12 hours of daylight and 12 hours of night on an equinox on that date. That happens twice a year, okay, where the sun's vertical rays are right over the equator. Okay, so we had the summer, then we had the, autumnal equinox, and then we had the winter solstice. Well, another 3 months, and we've got another equinox, okay, another equinox, and this one is the vernal equinox. Turn the page here. Vernal equinox. So they call that the spring. Vernal means green, where things are growing and becoming green. So that's the spring equinox. So that's March 21st, 22nd, okay, one of those 2 days. March 21st will be fine if you needed to remember one. And again, once again, we get the sun's direct rays or vertical rays directly above the head on that date, March 21st, at the equator again. So the Earth's neither tilted toward or away this time. So you're hitting right at the equator, okay? And then another few months and we're back to a summer solstice. And so that's sort of the cycle of the seasons. It has to do with those sun angles changing and the length of daylight changing, okay? And on those equinoxes, you got 12 hours of daylight, 12 hours of night, even right here in Monticello, good old Monticello, on an equinox, is going to get those 12 hours of daylight, 12 hours of nighttime. Okay, and so that's sort of looking at those direction of the sun angles, right? The vertical rays being intense or very low. And here is looking at, I don't know how well that's coming in for us. Maybe I'll try to focus it. Don't know if that's going to do any good. No, not really coming in too well. But we can see the tilting of the axis here, okay? And how that's going to change over time. And so let's just start over here with the December 21st. So in the northern hemisphere, we're thinking northern hemisphere since we live in the northern hemisphere. On December 21st, this is known as the winter solstice here. But noticing how the sun's direct rays are over that 23.5 degrees south latitude, that Capricorn, the Tropic of Capricorn, right there. But also notice your illumination circle here, right? The North Pole is in total darkness, right? So it's getting 24 hours of darkness at the North Pole, right? And smaller hours of daylight here. But as you go across the equator, which gets 12, you start to get more and more. And look at the South Pole. On the December solstice here, it gets 24 hours of daylight. The Southern Hemisphere is having their summertime. So these seasons are opposite between the hemispheres, right? They're getting total 24 hours of sunlight way down there of the, sort of south of the Arctic Circle, right? Antarctic Circle, Arctic Circle. And so it is opposite with these seasons because of that tilt. Okay, and that's at sort of the December solstice. And then, 3 months later, we get the sort of March equinox, so the vernal equinox or the spring equinox. Sun is vertical at the equator, right? So the sun's direct ray, you can't see it very well here, but it's right at the equator, okay? And so, going on around, we've got equal daylight, equal darkness, 12 hours, 12 hours, sun right over the equator, right? And then we come on around 3 months later and we're at the June 21st solstice, and this becomes our summer solstice here in the northern hemisphere. Your sun's rays are going to be vertical, meaning directly overhead at this special latitude, 23.5 degrees north. We mentioned that before. Kind of look at your circle of illumination. Now at the North Pole, so north of the Arctic kind of circle, you are getting 24 hours of daylight. Summertime, yeah, that makes good sense. They do. They get a period in there of 24 hours of daylight in this, summer solstice. But look down here in the southern hemisphere at the pole. They are getting 24 hours of darkness. So on the June 21st solstice for the southern hemisphere, that is their winter. It's our summer here in the northern hemisphere. 3 months later, then you can't really see it from the front there, but once again, we're at an equinox, so twice a year we have it to where the sun's direct rays are right over the equator, okay? And so that's called an equinox again. This is the September 23rd, or 22nd, 23rd date. And for us in the northern hemisphere, that's going to be the autumnal or the autumn or the fall equinox, okay, in there. So the sun is vertical at the equator again. And then, another 3 months and we're back to a winter solstice here in the northern hemisphere. Of course, this does vary between hemispheres in there because which one's got, the higher sun angles and the longer durations. It's kind of flips between us because of that, tilt to our axis of rotation. And this is looking at the length of daylight, I think, going on here. So that should be under here for kind of letter B. That's the winter solstice, right? You're looking here, we're getting like 9 hours of daylight at, say, 40 degrees latitude, a mid-latitude in there, where north of the Arctic Circle, which is the 66.5 degrees there, they're in total darkness. Yeah, so this is definitely a winter kind of solstice for the northern hemisphere. But opposite for the southern hemisphere, look down here at the pole, 24 hours of daylight, right? And so they're getting their summertime there. So the seasons are kind of reversed. Over here for a summer solstice in the northern hemisphere, notice how you're getting very long lengths of daylight, 24 hours north of the Arctic Circle, 13.5 hours at mid-latitude, 15 hours at, say, 40 degrees latitude. So we are getting onwards of 14 to 15 hours long duration of daylight, very high sun angles at this time of year. So it does translate into the warmer temperatures in the summer solstice for the northern hemisphere. And then, of course, the spring and the autumnal equinox, so twice a year on those special dates, we're getting the sun's vertical rays, 90-degree angle directly above the head at the equator. That's the highest sun angles at the equator then. And notice that the daylight and nighttime, so equal night is an equinox, getting 12 hours among all of the latitudes, because at that point the earth is neither tilted toward or away from the sun, and so it's sort of equal day and equal night, hence the term equinox. Okay, there. So that happens on the spring and the autumnal equinoxes as well. So special dates that we have. But again, all of these are compounded by one, the sun angle. So the higher the sun angle, the more intensity. The lower the sun angle, less intensity of solar radiation, and the length of daylight. And that does change from a winter solstice to a summer solstice to an equinox. So Those changes, the combination of those changes that are brought about because of Earth's tilt, that 23.5 degree tilt, does culminate into our seasons. Okay, and so those dates you do want to, be familiar with those couple PowerPoints in there. As far as where is the sun striking directly overhead, what special parallel of latitude, Tropic of Capricorn, Tropic of Cancer, at the equator, and match up those dates for your seasons, winter solstice, summer solstice, those equinoxes. What are those dates? So make sure that you've got all of that, what's going on with the amount of daylight. So really do spend some time studying those few PowerPoints in there. Okay, and be sure you've got that under your belt. And as always, ask me questions if you've got any. Be sure to get with me. So atmospheric heating, how are we getting the atmosphere to be heated? It is actually heated from the bottom, from the earth, upward. Okay, and so heat is transferred. It's got a gradient that we talk about from warmer to cooler objects. That is a gradient. From high areas of high temperature to areas of low temperature. That would be the direction that heat would want to flow. So it's always transferred from warmer to cooler objects. And so how's it doing that exactly? We've got some mechanisms of heat transfer. The first one, conduction through molecular activity. You need sort of direct atom to atom, molecule to molecule contact to get conduction of heat. Convection, this is a very important method of heat transfer in the atmosphere, those convection cells that we'll be talking about. But this is mass movement kind of within a substance. So here we're talking about the atmosphere, sort of fluid type of atmosphere, but it's a mass movement within a substance, and it does set up. Warm air wants to rise, it becomes less dense, so it wants to rise, and then it would cool off, because you remember the atmosphere cools as you go up in the troposphere, it sure does, and then that will cool off, and cooler air is more dense, so it will want to sink. And so we set up what we call a convection cell, and that's going to take warm air from the surface of the earth, move it on up into the atmosphere where it's cooler, and then we get a cell, we say, a convection. This is a very important process in the atmosphere, as we will see. Radiation, which is solar energy coming from the sun, it's called electromagnetic radiation. It has electric and magnetic properties to it, so they just kind of combine those words, electromagnetic radiation, and of course it travels at the speed of light. All electromagnetic radiation travels at the speed of light, so it doesn't matter which wavelength you have. They all travel at the same speed, 300,000 kilometers per second. This is radiation. So those are your three kind of mechanisms of heat transfer: conduction, convection, and radiation. So the heat energy coming from the sun will reach the earth through this electromagnetic radiation. Okay. Here we've got some pictures to kind of take us through those three mechanisms of heat transport. Of course, conduction, so think of metals. Metals conduct heat very, very well, but that's atom by atom, molecule by molecule. So as this hot pot's getting heated up, that molecule by molecule, the heat is going to be conducted to that handle, and that handle will get really, really hot. I don't know if you've ever experienced that, but yeah, you'll want to drop that because that's going to get really hot. Here we've got convection, so you're starting to see, this is a boiling pot of water here, but the same premise happens in the atmosphere. You've got that hotter water rising, it's a little cooler up towards the top, that'll cool off and sink back down to where you're setting up a little convection cell. So mass movement through a substance from where it's warmer to where it's cooler. Transport of heat. Kind of mixes it in that sense. Mixes the heat in the atmosphere as well. And then radiation, radiating out from a source. Okay, so radiation is another form of transfer of that heat. So those were our mechanisms of heat transport. So we do want to look at that electromagnetic radiation, just get a, a broad little understanding of those differences of wavelengths. And so we as humans do like to categorize things. And so even though the electromagnetic spectrum of radiation is a continuum, we tend to compartmentalize it kind of based on our uses that we have for it. So starting at the very, very short wavelengths, we do have, and it's kind of based on different wavelengths, but the gamma rays. Your gamma rays are those lethal gamma rays coming from the sun, but very short wavelengths. Okay, and we'll have a pictorial of the wavelengths in a second. X-rays would be next, so kind of know your hierarchy of the wavelengths. Be a little longer wavelengths are your X-rays, so in the medical field those are used. We've talked a little bit about the ultraviolet or the UV radiation as it pertains to skin cancer and different things like that, cataracts and that. A little bit of that still gets through our atmosphere, even though the ozone layer is really trying to block that out and absorb as much of that as possible. Then we get the visible light spectrum. Think of the colors of the rainbow, right? The visible light. That's what our eyes have evolved to be able to detect, the visible light. Visible light does a very good job of getting through the atmosphere. Nice little atmospheric window that the visible light makes it all the way to Earth's surface. In that kind of wavelength in there. And then even longer still are the infrared wavelengths. We talk about the infrared radiation as terrestrial radiation. So as the visible light comes in, things on the Earth are going to absorb that visible light, that shorter wavelength energy, and it will re-radiate it as heat energy. And we call that infrared radiation. So that's known as the terrestrial radiation. That's what everything's absorbing and then re-radiating it as infrared. Just a little bit longer wavelengths are the infrareds. And then your very much longer wavelengths, you got your microwaves. Of course, we use our microwaves, right, to warm up our dinner. And then radio waves are the longest of all. Okay, and we definitely, for our communication, use radio waves. So that's sort of the hierarchy of the electromagnetic spectrum. So kind of know which are the shorter wavelengths and which are the longer. So this is sort of the order that they do go in. Okay. And here's a nice little pictorial kind of showing you those wavelengths. So the really, really, really short wavelengths, right, are the gamma rays. Then we got the X-rays, then the ultraviolet. Here's our window of visible light. And then they've got that sort of, the violets and the blues are the shorter end of the visible light. And the reds are the longer portion of the visible light. So we've got a little spectrum in there of visible light, kind of the rainbow colors. And then we've got the infrared, right, a little bit longer wavelengths, microwave, and then we go on. They've got what? Television, FM radio, and then of course these long wave radio waves as well. So a change in the wavelength of your radiation as we go across the spectrum. Okay? Okay, so radiation, the electromagnetic radiation spectrum, of course, it's governed by basic laws. We have a few laws. They're not actually putting names to these, but these do have some chemical equations, some formulas, mathematical formulas that they use to explain these, but we're not going to go into that detail of it. But these laws of the radiation, they call them. And so, first one here, hotter objects radiate more total energy per unit than do cooler objects. So hotter objects, more energy. Makes good sense. So cooler objects, less energy. So that one, yes, that is a Stefan Boltzmann law. You don't need to remember the name, but hotter objects, greater energy. Makes good sense. The second one here, the hotter the radiating body, the shorter the wavelength of maximum intensity. So the hotter, okay, the body, the shorter the wavelengths. And that's like an inverse proportionality there, and that's known as Wien's law. You don't have to remember the name of that, but that's one of the laws. Hotter radiating body, the shorter the wavelengths of maximum intensity for the radiation. So hot objects have short wavelengths. Think of those gamma rays. Those are extremely short wavelengths. Those are lethal, damaging radiation wavelengths there. So hotter objects, shorter wavelengths, that makes good sense. And this last one here is known as black body radiation. So perfect absorber and perfect emitter of radiation. So those are objects that are good absorbers of radiation and good emitters as well. So they absorb all radiant energy and they re-radiate of that as well. They emit it, okay, as well. It's known as a black body. It has nothing to do with the color of the object, but it's just objects that absorb all wavelengths incident on them and emit at all wavelengths. So these are known as the laws of radiation. Okay. Incoming solar radiation. So here we have the atmosphere with a mixture of gases in there. And so it allows quite a bit of that solar radiation to go through, but it does do a good job blocking out, you know, the gamma rays, those lethal rays, the X-rays, right? Most of the UV radiation, ultraviolet radiation gets blocked, right? The ozone layer doing a good job blocking those things. All of the visible light comes through, so that's good. You know, some of the radio waves come through. There's another atmospheric window, we say, that allows some of those radio waves to come through, and that helps us with our communication. Radio wavelengths do. So they're talking about, you know, here atmosphere is largely transparent to the incoming solar radiation. But there are some things that happen as that radiation comes into our atmosphere. Three things here that can happen. We can get some of that atmospheric radiation to be reflected. This is a term that we call albedo. So albedo is the percent of that light that gets reflected. So what fraction of that incoming solar radiation gets reflected? This has to do with sort of the color of your substance. So clouds, being very light colored, will reflect a lot of that energy right on back out to outer space. Darker things like the asphalt, let's say the asphalt at the Walmart parking lot, that's going to absorb a lot of the solar radiation. So darker objects tend to absorb more. Lighter objects tend to reflect more. Okay, and this is known as albedo. And so that's a percentage of the light that gets reflected. Maybe a new term for you, albedo. Okay. Another thing that can happen is scattering. So it comes along, it doesn't really get absorbed, it just gets scattered off into a different direction. Okay. Absorption. It can actually then absorb that visible light. And once it does get absorbed, as I mentioned before, it re-emits it in a longer wavelength. That's the terrestrial radiation. That's in the infrared wavelength. Okay, so absorption, it's going to absorb it and retransmit that and emit it as infrared radiation. So absorption. So these three things can happen as that solar radiation is coming into Earth's atmosphere. Okay, and so most visible light, as I mentioned before, does reach the Earth's surface. We've got a little atmospheric window that does allow for all that visible light to come right on through. Okay. Now it's saying here, and they're going to have a little picture on the next thing here, about 50% of all that solar radiation that does come in gets absorbed at Earth's surface. About 50%. That's not too hard of a number to remember. So about 50% of the solar energy that strikes the top of the atmosphere will actually reach the surface of the Earth and go ahead and get absorbed and then re-radiated, right? Absorbed and then re-radiated. 50%. Not too hard to remember that one. Okay, and so here we've got a nice pictorial kind of showing the average distribution of the incoming solar radiation. So we got coming from the sun, 100% radiation. You probably can't see these small numbers here, but you'll have the PowerPoints. 100% of that's coming from the sun, right? But things are going to happen as it hits our atmosphere. We've got, about 5% backscattered, 30% lost to space by reflection, so albedo, and scattering, right? So here we've got albedo of the clouds, about 20% coming off of there. And so this kind of, the land, the sea, sometimes the ocean, that'll kind of vary depending on sun angle of how much is going to be reflected, the albedo on that. But all in all, we get about 50% of the incoming solar radiation to finally hit the land surface and be able to, and the sea, and be absorbed, okay? And then re-emitted as infrared radiation. Okay, so here it is. The Earth then, once it does finally absorb that, about 50% that makes its way to the surface, it re-radiates that radiation. We call that terrestrial radiation because it's coming from the land or the ocean, right? And it's at a little bit longer wavelength. It's actually in the infrared wavelength. If you look at your electromagnetic spectrum, the infrared are just to the right of the visible light. So it comes in as visible light, a little bit shorter wavelength. It gets absorbed and re-radiated as a little bit longer wavelength, the infrared. We call that terrestrial radiation, okay? The longer wavelength terrestrial radiation, so as it's trying to make its way back out, okay, from the Earth's surface, we've got some gases in our atmosphere. Remember we mentioned the carbon dioxide. We've got water vapor, right, up there. These guys, if you remember, will trap the heat. So what they do is they will absorb the infrared radiation. They are really good absorbers of infrared radiation, the terrestrial radiation. They will absorb it and they will re-radiate it back down to Earth's surface. In essence, sort of trapping that heat. So carbon dioxide and water vapor as well, okay? This causes then the lower atmosphere to get heated from Earth's surface upward, right? It gets heated in that manner, surface upward. This heating kind of effect, the heating of the atmosphere, is termed greenhouse effect because it's similar to a greenhouse. So you've got the glass in a greenhouse, right? You got your glass. Oh, maybe I can do a little drawing. The greenhouse effect. So maybe we can draw here, I don't know how well I'm drawing, but we've got the solar radiation, right? There's the sun. And you've got that coming in at fairly short wavelengths, right? The visible light, so short wavelengths. I'm using a little lambda, a little backwards upside down Y. Remember we used wavelength for our wave action? Well, we use that little symbol for wavelength. That is the visible light that's making its way through our atmosphere, coming into our greenhouse here. Oh, we got a nice flower or something in our greenhouse here, right? Well, happy flower. And that's going to absorb everything, every surface is going to absorb that shorter wavelength, okay? And then it's going to re-radiate that as infrared radiate, a little bit longer wavelength. So our little flower is going to radiate, and I'm trying to make that wavelength a little bit longer, okay? That is a longer wavelength. Okay, wavelength. That's the infrared. Okay, well, the glass, okay, windows there, will not allow that wavelength to go out. Okay, it cannot penetrate the glass. And so it just bounces all around in the greenhouse and continues to warm, and they re-radiate and warm and warm. It's the greenhouse effect. Well, our atmosphere is somewhat similar to this. So the greenhouse effect, if you've ever gotten into a parked car that's been in the sun, right? It gets really, really hot inside that car. It's because that infrared radiation can't make it out through the glass windows in your car, and your car just gets hotter and hotter and hotter as you go. It's kind of like what our atmosphere is like. Things block, okay? It's not glass windows, but it's carbon dioxide and water vapor and some other ones. Methane, I've got some few other ones up here that do the same thing. Nitrous oxide. So we got water vapor, we've got carbon dioxide, right? The CO2. Methane, remember we talked about the methane, the natural gas way back in the introductory chapter, the hydrocarbon fuels. Methane is a big greenhouse gas, we call these. Nitrous oxide as well. So these little gases that are in the atmosphere will actually block them from being radiated out to outer space, and it just gets re-radiated back down to Earth's surface, causing it to warm and warm. We do call that the greenhouse effect, okay? So that's kind of what's going on with the heating of the atmosphere. We do call that the greenhouse effect. And we do have some environmental concerns that we've talked about before. Human-induced environmental concerns about, well, that amount of carbon dioxide that we are putting into the atmosphere. I've got some updated information here. Find it. Yeah, the parts per million continuing to rise. So this is a human-induced. We are continuing to burn those fossil fuels. We're burning those hydrocarbons, and we are putting more and more carbon dioxide into the atmosphere. This is the 2020 update on the parts per million. It was 415 parts per million. And so in the kind of historical past of carbon dioxide levels, they've never gone, they have fluctuated, right? We'd have glacier, interglacial, glacial, interglacial periods where we would get fluctuations of our carbon dioxide. But right along here, 300 parts per million was the highest historically that it had ever gone. 800,000 years before today is this date. But along about the Industrial Revolution, when we began burning fossil fuels, we were, of course, a byproduct of burning of fossil fuels. Those hydrocarbon fuels is carbon dioxide. And so it began, kind of in that Industrial Revolution, began increasing and increasing. We continue year by year to increase the amount of carbon dioxide in the atmosphere, and currently we're at about 415 parts per million, higher than it has ever been in the historic past, at least back 800,000 years, right? So there is a nice correlation between the input of carbon dioxide and the warming of our atmosphere, the global warming kind of issue. So, you know, it is a concern that we're continuing to warm the planet, and it's something that humans are doing, okay? And so they do call that a human-induced environmental problem. So, you know, what would be the problem of having, you know, the global warming, the climate change? Well, I've got a few things here. Your temperatures, of course, are going to rise. It is going to affect your storms. You're going to have more storms and more intense storms. So the hurricanes and the intensity of the hurricanes, the flooding, the intensity of the flooding. On the other end, you might get more or worse droughts. And those droughts, of course, are going to cause more or worse forest fires. So we are having those wildfires that have gotten worse and worse and worse. Heat-related illnesses on the increase, economic losses, rising of sea levels, right? So we know what can happen when we rise the sea levels. A rising of the sea levels, encroaching in on our continental shelves, and more flooding going on. So more animal extinctions, right? So many things to be concerned about with the global warming situation. So this is just a little pictorial showing you the shortwave radiations come right on in through the Earth's atmosphere. That's sort of a atmospheric window that allows that visible light to come in, which is a little bit shorter wavelength. No problem. It comes in, makes it down to Earth's surface. The Earth's surface then re-radiates that. It absorbs it, re-radiates it as a little bit longer wavelength. Terrestrial radiation, the infrared radiation, remember that? And then we've got the gases in there, the carbon dioxide. There's a little carbon dioxide molecule. Here we got a little water molecule. Those primary, greenhouse gases in there, they will absorb the infrared radiation, terrestrial radiation, and re-radiate it back down to Earth's surface, in essence continuing to warm the atmosphere. Kind of like a little cycle that happens. So yeah, greenhouse gases re-radiate some energy earthward, and that's trapping the heat in the lower atmosphere. Those kind of look like little honeybees or something, but they're supposed to be the carbon dioxide and the water vapor, those greenhouse gases. Okay. And so this PowerPoint in here is kind of an old one because it only goes to 2008, but I showed you the one that went to 2020, and so we are now, so back in 2008, where were we? We were just a little over 380 parts per million. So in that span of about 12 years, we've gone up to 415. Okay, continuing to rise, continuing to rise. So yes, it is concerning because we're continuing to warm the planet. And this is sort of showing you the global temperature changes. And so what they've done, sort of averaged this over 30 years here, which that's what they do for climate, is tend to average it over 30 years. And so they've got from, 1860 to 2000, it looks like. But what they did was they took from 1960 to 1990, the average temperature, and this is global temperature, and they made that their zero line, okay? And then down here, those would be temperatures that were less than that average. And then along through here, we're starting to see the warming trend, okay? We're starting to see where we are having continually increasing, and I think 2016 was like the warmest global temperature to date. So continuing to rise. So that amount of carbon dioxide is being translated into warmer global temperature changes, and not just in the atmosphere, but also in the ocean, because the ocean is going to try to absorb some of that heat as well. So the oceans are getting warmer too, and that's also of concern. So that's a little bit on the greenhouse effect, and so that's how sort of the Earth's atmosphere is warmed from the surface upward. Okay, so as I mentioned, our meteorologists love to take temperature measurements, and so we do all sorts of manipulation of the data. So daily maximums and minimums. We do daily mean temperature, so the average temperature per day, what the daily range is, what the monthly mean, so now we take it out for a month, the annual mean, so what the average over a year is, and annual temperature ranges, so have from lowest to kind of highest temperatures annually. So they do a lot of sort of manipulation and data calculations for all of these. They really are data hungry people, our meteorologists are. So we've talked a bit about sort of latitude kind of controls of temperature, depending on what latitude you were at the poles, are you over at the equator, a little bit about that. How much solar radiation is being received, that's probably number one in controls of temperature, just how much solar radiation is getting absorbed. That's your most important control, but there are some other controls as well that are important. So some temperature variations. First one here This is actually very important, and we'll learn a little more about it in coming chapters, but differential heating of land and water. So land will actually warm up a lot faster and to much higher temperatures than water does. Water actually has a very high, what we call specific heat, okay? And so it needs to absorb a lot of energy before it will actually increase its temperature. This sort of specific heat of water. This is very high for water. Land, not so much. So land's going to heat up more rapidly than water, and it's going to get to a higher temperature than water will. Okay, and then of course it's going to cool off a lot faster than water, to lower temperatures than water. And so water is a very great mediator of temperature. So it actually kind of stores some of the heat. It's called latent heat. It's a term that'll be talked more about in chapter 12, but I'll introduce it here. Latent heat, so heat that is stored or released by phase changes of water. So as water is going through physical states from solid, liquid to gas, it will store or then release energy. So as it goes through its physical processes, you know, it goes through condensation or evaporation, it's going to store or release this heat energy, okay? So heat that gets stored or released by phase changes of water is termed latent heat. Like this hidden heat. So we've got a very high specific heat for water. It takes a tremendous amount of calories or heat energy to warm up 1 gram of water 1 degree Celsius, okay? And so it takes much more heat energy to get water to warm up and to cool down, to release it. It's very slow, than land does. And so you get this differential heating of land and water. Water tends to moderate a location. So depending on, and they call that kind of marine or mariner, kind of maritime, here it is, influence on temperature. So being near a water body, and depending on what direction the winds are, if the winds are offshore onto shore, that direction, that will really moderate your temperatures. So here we have 2 locations kind of showing that maritime influence of the land. They're basically at the same latitude. We've got Vancouver, you probably can't see that too well, and Winnipeg. Winnipeg is more interior of a continent, and Vancouver, up there in Canada, more coastal, okay? And so they're looking at the variation of temperature over the year. So there's the months of the year, January, February, March, and so on to December. And then we've got temperature in Fahrenheit on this side and temperature in Celsius on the other side. Well, the red kind of line here, let's start in January. This is Vancouver, the maritime or the marine location. It goes up, we get a little warming, and then we come back down. Not too much of a range here. So the being close to the water has sort of mellowed those temperatures, moderated those temperature swings over the year. Here, Winnipeg is a continental location. Look, it gets really, really cold there. Okay, and then in the summer months, it gets really, really hot there. And then really, really cold again in December. So very large temperature range, okay, for a continental type or a land-based region. So having, you know, a city kind of near the water, so the annual temperature range for a city kind of near a coastal region like Vancouver, will be moderated by that proximity to water. Okay, that latent heat is really warming up slower and cooling down slower, so it moderates the temperature of a region close to it. Okay, even though latitude-wise, those two locations should be receiving the same amount of solar radiation, right? They're in the same latitude, and so they should be on an annual basis getting the same amount of solar radiation throughout the year of variation. So yeah, that's one thing, but being near water is another one. It has a moderating effect. We call that a maritime influence on temperature. So land versus heating, a differential of that heating. Okay. And of course, the continental ones are going to be sort of the highest temperature swings, okay, because that land's going to heat up and it's going to cool down very fast. So you get large temperature swings in the continental regions. Another thing, so altitude. So elevation, altitude. Well, I can think of a mountain range right there near the equator, Tanzania, Mount Kilimanjaro. You've got snow caps, you've got glacier actually on the top of that mountain. That's a very tall mountain range, very high altitude, but it's right there at the equator area, you know, high sun angles, warm temperatures year round, yet it's got glaciers there up on the mountaintop. So yes, mountaintops are going to have much cooler temperatures, right, at the altitude of our mountain ranges as compared to the lowlands, right, down below. So an altitude can definitely, as you go up in elevation, temperatures do decrease in the vertical. So yes, altitude can make a big difference, right? The tops of the tall mountains are colder than the surrounding lowlands because of an environmental lapse rate. If you remember that 6.5 degrees Celsius per kilometer of cooling that happens as you go up in altitude. That's what's going on, that environmental lapse rate. Your geographic position, so latitude, as we talked quite a bit about, you know, being near the equator, you're going to have those higher sun angles all year long sort of thing. You're really going to have swings in temperature at your poles, right? So in the summer months at the North Pole, right, at summer solstice time, you can get 24 hours of daylight, so lots of solar radiation, versus it being at the South Pole, 24 hours of darkness. So yeah, your geographic position or your latitude is going to make a difference on amount of solar radiation. Just how much cloud cover are you going to have? Because if you remember, cloud cover will act. It's got the water vapor in the clouds, the little droplets of water vapor, right, in your clouds, which water actually does absorb carbon dioxide and re-radiate it back down to Earth's surface, so the greenhouse kind of effect going on. But there's a couple things cloud cover's doing. Cloud cover's going to really control temperatures, really moderate your temperature. So during the day, if you have cloud cover, it's actually going to reflect by albedo, that next term. It will reflect a lot of that solar radiation, so your temperatures won't get too high. And at night, it will actually trap in a little bit, almost like a blanket, will trap in some of that heat at night, so with a cloud cover. If you didn't have the cloud cover, all that terrestrial radiation will kind of work its way right on out to the atmosphere, to the space, re-radiate it out. Kind of radiational cooling would happen. If you got a cloud cover, it's going to act as a little blanket and radiate some of that warmth back down to the Earth's surface, so your lows won't get too low during the night, and your highs won't get too high during the day. Cloud cover very much can moderate your temperatures. And of course, albedo, what your surfaces are like. I had a little picture for albedo here from your book, page 344 of the 8th edition, figure 11.2. Yeah, just depending on how thick your clouds are, you know, 70 to 90% reflection, thinner clouds, 25 to 30. Actual water, you know, sun angles with the water, 5 to 80, just depending on what the sun angle is for reflection off of water. Here we have asphalt, so 5, 10% reflection because it's going to want to absorb. Darker colors will absorb more, so it's not really reflecting too much. Your grass as well, 5 to 25% albedo on that. So yeah, the albedo will kind of, are you in a city that's going to absorb a lot of that heat energy, or are you in a region where you're going to get a lot of reflective, near body of water kind of thing, to reflect some of that solar radiation. So albedo, yeah, does have an effect to control kind of on temperature as well. So clouds reduce the daily temperature range. So here's like during the day, panel A, it's going to act to reflect with that albedo, reflect some of the solar radiation, and at night it's going to trap some of that terrestrial radiation and keep re-radiating it back down. As you can see, it's trying to go out, but it gets re-radiated back down because of the cloud cover, almost like a little blanket, trapping in some of the heat at night. Okay, so that will reduce your daily temperature range. Okay, your cloud cover. Nice moderation. Okay, world distribution of the temperature. So we've got some temperature maps, and we'll look at, they've got some contours on there, and we've talked about contours. If you are in lab, we talked quite a bit about contour lines, which were equal lines of elevation on our topographic maps. But these lines are called isotherms, and so these are temperature. Iso meaning equal, therm meaning temperature. So lines of equal temperature are what isotherms are. So it's a line connecting places of equal temperature. So anything along that line would have the same temperature. That's an isotherm. And of course, temperatures are adjusted to sea level. And we've got two panels, two maps. One's a January scenario, and the other one is a July scenario, so seasonally quite different. Are used for analysis because they represent the temperature extremes, kind of like the largest kind of difference we would see over a year, kind of globally, these are looking at. So kind of globally, our temperature patterns, the temperatures decrease poleward from the tropics, and that does make pretty good sense, right? Because of course sun angles are going to get a little lower as you go, towards the poles, right? And so warmest temperatures, out through the tropics, which is about, straddling your equator there. And of course, coldest at the poles, right? So temperatures are going to decrease as you go towards the pole, north and south latitudes there. We will also see a little shift in the latitudinal shift with the seasons, because if you remember, our summer solstice, okay, here we are, here's the sun in the middle if you remember that. Our summer solstice is where we have the highest, right, direct solar radiation, vertical solar radiation, right over 23.5 degrees north latitude, right? The Tropic of Cancer. That's like our northern hemisphere summer. And so you're going to see on these maps, sort of in the July map, that your warmest temperatures are a little bit, okay, to the north of the equator, right? You're going to have your warmest temperatures there, cooler down in the southern hemisphere. And then as we kind of go through the seasonal kind of change, right, if you remember, when you get to over here, here's the sun, and you're having a tilted away, the southern hemisphere getting the direct solar radiation at 23.5 degrees south latitude, Tropic of Capricorn, that is our northern hemisphere winter. Southern hemisphere is having their summertime, but that is our winter time because we're tilted away. So you are going to get latitudinal shifts with seasons. So you're going to see that between the July and the January maps in there. You'll also see that the warmest and the coldest temperatures occur over land. So your highest temperatures, your lowest temperature, remember we've got some very high specific heat for water. Water's going to be kind of moderated, but the land is going to have your greatest temperature swings. So your land is going to get the hottest temperatures and the coldest temperatures. Cools off the fastest, right? Warms up the fastest, and to higher temperatures and to lower temperatures. Biggest swings, annual ranges, are with land, okay? Water's more moderating because it takes so much heat energy to get it to actually change temperature. So we are going to be seeing some latitudinal effects with the seasons, and land versus water sort of changes with those as well when we get to that, those images. Southern hemisphere, you're going to see isotherms that are straighter. Now your southern hemisphere has mostly that water, right? It's sort of the water hemisphere, if you remember that. The isotherms are more stable because water is more moderating effect. So southern hemisphere, sort of that water sphere, you are going to see straighter isotherms, not such a range, and more stable in there. The isotherms also kind of show those temperature ocean currents as well, because temperature, right, is going to go right along with the ocean currents, the circulation that happens. It's related to the atmosphere. Annual temperature range, not too great at the equator. That's fairly stable throughout the year as far as sun angles and sun duration at our equator. Of course, that's going to increase with an increase in latitude. The higher latitude you get, the greater swing in temperature range, annual temperature range happens as you get towards, the poles. Because if you remember, we had 24 hours of light, 24 hours of darkness, and so that ends up making a really great annual temperature range at your poles, right? And of course, that's also going to be the greatest over continents, because continents, land's going to heat up more and cool down more than water will. So yeah, your annual temperature ranges. So over the year, how your temperatures are going to be high to lows kind of thing. Smallest at the equator, increasing with an increasing latitude. So your poles are going to have the greatest temperature ranges. And greatest temperature ranges annually over a continent, right? Because that land is going to heat up more and cool down more than, say, water would. And so kind of just looking at it, here we have the January scenario. And so it's kind of color-coded for us, but we've got degrees here of temperature. And so this is in Celsius degrees. Just noticing here how kind of straight it is towards the southern hemisphere, that water hemisphere, not too, wavy there. They're pretty stable. But you do get up in here in the northern hemisphere, the land hemisphere, right? You do see kind of a swing in the temperatures, right? You're getting, of course, higher temperature over here on the land across the equator. So latitude-wise, yeah, you're going to have, some very warm temperatures across the equator here. And so this is a January one. You'll want to notice as we switch here, but your highest temperatures are about 23.5 degrees south. That's where the noon sun angles are highest, right? Directly overhead. So here we are at about 20 degrees south latitude, right? This would be the Tropic of Capricorn, right? That would be like a winter scenario for the northern hemisphere. But look, you have your oranges here are your warmest temperatures. Of course, warmest over the land, as you can see there, this darker red interior of the land, right? But that's sort of in the southern hemisphere here at 23.5 degrees south, because that's where the sun's highest angle is. Direct sun rays are right there. So this is a January scenario there. And then we're going to switch to a July scenario. And right away, notice how now those warmest temperatures are, and that's 20 degrees right here, 20 degrees, so 23.5 degrees north latitude, right? The summer solstice, this is the Tropic of Cancer. So your sun are the direct rays right over the Tropic of the Cancer during the summer solstice time period. And so now you're seeing all the warmest temperatures right there in the northern hemisphere. Once again and again, highest temperatures over those sort of internal continental land masses. Right in there's United States, right in through there, right? China on over that way. And so, yes, you're getting large temperature swings there, but that's July. So we've got latitudinal shifts, we've got land versus water sort of scenarios happening here, but sort of a average change between a July and a January. And these were known as the isotherms, right? So lines of equal temperature. But that's just a sort of a comparison of how those do go through changes, sort of a yearly changes in temperatures. So talk lots and lots about the temperatures in this one, the heating of the atmosphere. And of course in chapter 12, we're going to look a little more at that humidity, so the moisture, cloud formation, precipitation, those processes for precipitation to actually happen. So we are going to continue with our talk about the atmosphere, our beautiful, beautiful atmosphere. So that does conclude chapter 11, and I will see you next time for chapter 12. Thank you.